This lecture is going to look at Chapter 3.4, Artificial Starting Solutions. In the last lecture, we looked at the simplex method. And the simplex method is quite powerful, but it only works in certain cases. Your linear program has to look a certain way. It has to be a maximization program, and the constraints all have to be less than or equal to constraints. We don't always have that. For instance, in this problem that we have here, we have a greater than or equal to constraint. We have an equality constraint. So we have seen that we can rewrite this with surplus variables. x1 plus x2 minus s1 equals 4. We can rewrite our second one as x1 plus 2x2 plus s2 equals 3, a slack variable as we're used to. And the third one, we have an equality, 2x1 minus x2 equals 7. Now, in cases where we have like this, we have to go one more step. We have to introduce something called artificial variables. So for instance, for our first one, that one has a surplus variable. We're going to introduce an artificial variable. And we're going to have plus a equals 4. Our second one is in the form we need, plus 2x2 plus s2 equals 3, because that had the slack variable. The third one is an equality, so we have to introduce another artificial variable, 2x1 minus x2 plus b equals 7. So we've had to introduce two artificial variables. And what we're going to do is we've got a couple of methods that we're going to see to handle this case where we have artificial variables. Really, the simplex method demands that you have slack variables. That in every constraint, you have plus something, where that something only appears in that equation. So when we have surplus variables or we have an equality, that doesn't happen. So we have to artificially introduce that. For instance, in our first one, we have plus a only appears in that equation. The second one, we have plus s2 only appears in that equation. In the third one, we have plus b, the b only appears in that equation. That is what we need for the simplex method to work. And if you recall how it works, these are our basic variables. So we need basic variables, which is one variable in each equation, which appears only in that variable and has to be plus that variable. So it has to behave like a slack variable. So that's the idea of artificial variables. Now, it takes a little bit of getting your head around the artificial variables and what they are. You know, what are they? They're things that we are introducing artificially. They aren't really part of the problem. If they were to be anything other than 0, it's going to cause issues with our solution, because these are things that we've thrown in. So the challenge now is we've put these artificial variables in so that the simplex method can work, but they aren't really things that are there. They can't have any value. We have to ensure that they're all equal to 0. And we've got a couple of methods of doing this. So now we have a linear program with a few variables that are not only going to have to be non-negative, but they actually have to equal 0 themselves in the end. So we have two things that we're going to do to see this. The first one is called the M method. So here's a linear program with two greater than or equal to constraints. So we introduce our slack variables, and then our surplus variables, and then we introduce our artificial variables. So we have plus a in the first one, plus b in the second one. But now the problem is that a and b have to be equal to 0. So how can we do that? Well, here's a little trick. Here's a trick that we do. We are going to maximize that, but we're going to add the artificial variables in. We're going to do this. We're going to maximize negative MA minus negative MB, where M is a very large positive number. So in other words, we are going to make sure that this new part, even if A and B were tiny numbers, tiny non-zero numbers, because remember they have to be positive as well, even if they were tiny, tiny numbers, it is going to dwarf everything else, and it is going to make sure that so when it's in like this, it's going to make sure that the value of those are zero, because if they were anything other than zero, it would dwarf everything else in there. So by adding into our maximization the negative of our artificial variables times a very, very large number, that is going to guarantee that they become zero. Because if they're anything other than zero, we're not going to get a maximum value. We're going to get something that's much, much, much smaller, much more negative. So that's the thinking behind the little trick. Now, generally when we solve this, we leave the m in as an algebraic number, just recognizing that it is going to be much larger than anything else. In the book, they actually say, well, let's find a number that works. So here we're dealing with numbers 2, 3, 4 in this problem. If you set m equal to 100 or set m equal to 1,000, just put that number in for m and it's going to work as well. Both methods work. I'm going to talk about doing it algebraically, where you don't actually put a number in for m, you just recognize that it is an extremely large number. But the book does give a slightly different approach for it. I like to do it this way because there are times when doing it the way of the book, it can run into problems and you have to redo things. So here's our problem. We have introduced the artificial variables and we have made them extremely large negatives in the objective function, with the idea that they're going to go to zero. Otherwise, they're going to dwarf everything else. So we have our tableau. We put everything in our tableau. Now, here's the problem. If you remember when we put together the tableau, we had our basic variables, but in the tableau, there were zeros. Our basic variables did not appear in our objective function. Because of what we've done for our objective function here, our basic variables, the a and the b, are appearing in our objective function. We can't have that. We need to get them out of there. So how do we do that? Well, take a look at what you have in your constraints. Each of your basic variables appears in a single constraint, and those constraints are now equalities. So we can rewrite those constraints, and by rewriting the constraints, we can make an equality for each of them and get rid of them. So here we have our maximization function. We have our constraints. Rewrite those constraints where a equals something and b equals something. That's all I've done here. Now I can take that, substitute it in there, and I get rid of my a and b. So when I substitute my a equals that and b equals that in my objective function, calculate it all out, remembering that the m is still in there, we get a new equation to maximize where we have our surplus variables in there, that's fine, but our basic variables, the artificial variables, the a and the b, are now gone. Now we are in a format that we can solve. So that gives us this tableau. And you see now I have the m's in there. Now remember what the rule says. When you're using the simplex method, you start out by finding the largest number in your objective function row. So what's the largest number in here? It is going to be this one. Because remember, m just represents an extremely large number. So that number is 4 times m minus a little bit, but it's essentially 4 times m. The others, under x2, that's an m. Well, it's not as big as 4m. The other two are negatives, so you want the positive number. So the one with the 4m, because remember, m dwarfs everything else, that is your largest number. So that is your pivot column. Then you find your pivot row the same way. You take your ratios, take the smallest one. That means that gives us as our pivot element. Pivot a few times and you're going to get your answer. When you get your answer, your artificial variables become non-basic. If at the end of your pivots you still have an artificial variable that is basic, that means there is no solution. So when you're done your pivots, make sure that your artificial variables are non-basic. In other words, they've moved to they're on the left side of your tableau. If not, there is no solution. If they have moved there, you can just read off your solution. And that's what this says, that when the problem is infeasible, in other words, when there's no solution, you will get an artificial variable that stays as a basic variable. Here is a problem that is going to give you an infeasible one. Try this. Try the M method on this. It doesn't take too much work to do it, but go through the steps for it. Practice this. Okay, the M method is one way of doing it. In the situation where we have these artificial variables, there is another way we can approach it. This is called the two-phase method. It's the same thing as the M method. It comes out with the same answer. In fact, if you look at it more closely, you can see that the M method and the two-phase method are actually doing the same thing. You're just kind of presenting it in a different way, and you have slightly different tableaus. But we have the same problem. We have the same challenge. We have these artificial variables. We have to guarantee that they are equal to 0. So what do? Well, if we were to, here is our problem with the artificial variables. If we were to take this and just solve it out without worrying about the artificial variables, what do we get? Here's our solution. We get non-zeros for our artificial variables, which is an issue because those aren't really variables. They have to be equal to 0. So how do we get them equal to 0? Well, if you recall the M method, by setting a very large number times those variables and subtracting it, making it negative, we guarantee that they're equal to 0. Well, here's another way of guaranteeing they're equal to 0. In the two-phase method, we aren't going to introduce variables of unknown size. We are going to use that problem, which is the problem with the artificial variables, but we are going to first, for phase 1, change our objective function. Because remember, what we're trying to do is we're trying to get A and B equal to 0. So what we do is we set up an auxiliary problem. We take our objective function and we replace it by a simple function that says minimize A plus B equal W. Remember, A and B have to be greater than or equal to 0. So when is A and B minimized? When they're both equal to 0. So first thing we're going to do is solve this to make A and B equal to 0. We had to minimize a plus b equals 0, but we want things to be maximization. So here's a trick. Minimize a plus b is the same as maximize negative a minus b. So that's a very simple trick to turn minimizations into maximizations. Subject to, and there's our constraints. When we do that, we get our tableau. Now, what are we going to do next? Again, we have the issue where our basic variables appear in our objective function. So we're going to do that same trick. We're going to use our constraints, which are now equalities, to get rid of them out of there. So we turn our objective function, we get rid of the a and b by using the equalities in our constraints, and we now have a new objective function. But this objective function is the same thing as minimize a plus b. So really what we're doing is we're coming out with a solution, an interim solution, where a and b equal 0. We aren't worried about maximizing our original function yet. We are just working on making a and b equal to 0. So now we've rewritten our objective function to guarantee a and b are equal to 0, put it into the tableau, and solve. When you solve that, you are going to get a value for x1 and x2, assuming that it is feasible. In this case, if you solve this, good idea to go through these steps, you are going to come out with the solution of x1, x2 equals 10 over 7 and 2 over 7. So this is the end of phase 1. What is this? This is a feasible point where a and b equals 0, and it's a place to start your simplex method. Note that at this point, the solution of the objective function is 0 when you solve it out. So here's what we had for our objective function, or our tableau, at the start of phase 1. When you solve it out, you get this. You actually get a 0 here. That is our tableau after phase 1. This gives us a starting point for phase 2, and now we are going to go back to our original objective function and solve that one. So we have to solve 2 linear programs here. The first one to guarantee our artificial variables are 0. Now that we have artificial variables equal to 0, we're going to go ahead and solve our original one. So how do we do that? This is the tableau that we ended up with at the end of phase 1. What we do now is just drop our artificial variables. So we have these artificial variables. We just get rid of them. Drop them from the tableau. What do we end up with? We end up with this tableau. So we can simplify it a little bit. Now what do we have? We have a linear program at this point that has a starting point, and when we jumped from the top one to the bottom one, notice what we did. This was our objective function to guarantee a and b equals 0. We now go back to our original objective function and put that back in. Our original objective function here was to maximize negative 2x1 minus 3x2. Notice that that is back in here. So at the same time as we drop our artificial variables, we replace the objective function with the original one, which is what we're trying to solve anyways. Now, we still have the same old problem that we had before. This time our basic functions, if you just look at this, our basic variables are x1 and x2. They're the ones that form the basis. They're the ones that appear uniquely in each equation. You can take this tableau and rewrite it as a linear program, which is what we did here. So I just took it and rewrote it as a linear program. Notice that the x1 and x2 are unique in the two constraints. So we can rewrite that as x1 equals something, x2 equals something, and substitute the x1 and x2 to get them out of the objective function. Because at this point they're basic variables, we want our objective function to have only non-basic variables. So after we do that substitution, we end up with this, which we can then put back in the tableau and use the simplex method. Now, what does the simplex method say? Find the largest non-negative number in your objective row. Well, in this case, we actually don't have that. We are already at our solution. Usually when you do this, you'll have to go through another step. If you look at the example that they have in the book, in the textbook, doing it, they actually have another step. Okay. So the two-phase gives us another way of solving linear programs when we have artificial variables. Now, there's a complication with this. When we have the two-phase method, when we do it, you remember that we ended up with our artificial variables at the end of phase one. Our artificial variables had become non-basic. So the basic variables in the example we saw before were x1 and x2. They were some of our original variables. They could be the slack variables or the surplus variables as well. But the key is the artificial variables have to be on the left-hand side of your tableau. All the artificial variables have to be non-basic. Sometimes you'll go through phase one and you will end up with one that is one or more that are still basic variables. When that happens, it doesn't mean there's no solution. It does mean that you have to do something extra. You have to turn one of those, you have to turn the basic artificial variables into non-basic. And there are things you can do. Really what you're doing here is just a substitution. So here is the steps. When that happens, you select an artificial variable that's in your basis and designate its row as the pivot row. Choose any entering variable that is a non-artificial variable with a non-zero coefficient in the pivot row, and just do the simplex iteration. That's going to put the artificial variable into the non-basic. And you just keep doing this until all of your artificial variables have been removed from the basis. Now this step in the problems that I'm going to give you for the assignment, there will be one of these to try out. Okay. It is something to keep in mind when you're doing the two-phase method. Okay, that's it for the big M and two-phase method. Practice these. The book has more samples. It's a good idea to get used to what's going on with these methods.